Yeah, that's just so ugly. Okay, well, that's all right. So just finishing up the last bit about the liquid crystals. Um, these crystals, especially the cholesteric ones, the one that had layers and then they kind of rotate for other layers, those can interact with light, and we can use them to produce. Is that so? We can use them to produce images and that sort of thing. 1 second, sweetheart. What's up? He of course waits until class starts before he's gonna start being naughty. You're okay, sweetie. Okay, these things will, they can alter their orientation. Yeah, right. So, interesting thing. His tongue sticks out on the right side. His sun sticks out on the left side. Um, so there you go. There's your lesson for the day. So these alter their orientation when the temperature and pressure change. And so we can take advantage of these crystals to use them in things like televisions or monitors or whatever, where we can have a slight temperature change to them that alters the directions that they're facing, and that'll kind of change the light patterns that are coming out of there. So you can change the color, you can change whatever you're looking at. So these can be used for imaging. So whether that's a TV or a monitor, or we can use these for thermal measurements. So say that you want to, have a thermometer that is very specific. You could use liquid crystals to kind of to do that. So you can see the way that they're altering the light. Some instrument could pick that up, and you'd be able to get a very accurate measure of temperature. Or you can put it on a film and have thermal paper kind of work this way, or electronic paper work this kind of way. Or you can make it into little patches that you could stick on something, or make a mood ring out of them. I mean, you can have all sorts of things that are temperature sensitive, with liquid crystals. So there we go. So there are our kind of applications. So really, I guess the only thing I would ask you about liquid crystals, though, would be, what components the molecules of liquid crystals would need. Like the rigidity in the polar portions. Kind of more just conceptual stuff like that. I'm not going to ask you the names of the different types. I'm not going to ask you about these kind of applications. So I would focus on what makes a liquid crystal. I guess that would be more kind of where you should guide your studying. Okay, cool. Any questions on intermolecular forces or liquids or those properties we talked about? I did put another homework up for you guys. It's a pretty short one. It looks long. I think it's like 7 pages, but you'll see some of these, it's one question that's multiple choice, takes up half the page, and it's a very simple circle the one that does hydrogen bonding or something. So it just looks long, but it's not. So that is up there on Canvas for you guys. You can take a look at it. It'll be due Sunday as well. So, but yeah, I'm happy to answer any questions if there are any that you guys have right now about intermolecular forces or liquids and stuff. Other than that, okay, we're on to our very last chapter then, which is on solids. And we're going to see that the majority of the tough part of this stuff is going to be geometry. So we're throwing you back into geometry land. Um, you'll have some nice geometry homework. So you're going to want to remember all your rules about triangles and that sort of thing, your Pythagorean theorems and bisecting lines and all the stuff you thought you could forget from 8th grade. Oh, really? Okay, so Tyler apparently is going to be very happy about this. So, first off, we're going to see that there's kind of a number of different ways we would end up with a solid. And so some of these would be ionic solids. Yeah, I know, but it's not going to be very advanced geometry. It's like Pythagorean theorem and then, understanding some angles and stuff. Most of the things will be 45, 45, 90 triangles. So it's there's not going to be a whole lot of sine, cosine, nothing like that. Not a lot of trig, but just more Pythagorean, I would say, is the big one. Okay, so we have ionic solids. We also have metallic solids. How many radians are in your shell? Oh, ugh. Let's never speak of radians to me. How foul. Arcs and radians and bleh. No. I don't remember any of the circular geometry at all, so forget it. Okay, something that's an ionic solid might look like this. Yeah, right. So I give you nightmare about sig figs, and you give me nightmares about circles and nasty chords and secant lines and bleh. Where we so in ionic solids we have positive and negative things there, and they will typically form very nice repeating structures that we're going to be studying. Metallic solids are going to be kind of similar. We're going to see there's different forms these might take, but they would just kind of also look like that. But instead of having positive and negative things, they're just all there. So they might just be nicely organized like that. And we're going to have different types of bonding that are going to be associated with these. We also have covalent networks, which is something like, for example, diamond, where we just have these big networks of carbons all bonded to each other, something like this. We're just this really big, completely covalent structure where we're just having tons and tons and tons of molecules. So, etc. These would all be connected to other carbons, and we would have massive networks like this, and things like that will be solid. And then the last one we have are molecular solids, which would be something like ice or sugar. These would be things that are held together with intermolecular forces. So this would be like for ice, you'd have all your water molecules arranged very nicely. I don't know. I guess I'll be consistent here. Let's see. Whatever, some way of making these look nice. I'm not very good at drawing, as we know. Whatever, we can fake it. And you'd have very nice kind of organized structures in molecular solids. But these are held together with, not that. That's a bad hydrogen bond. Shame on me. So you've got, hydrogen bonds here that are happening here as well. So, but these are not like full bonds, right? These are just intermolecular forces. So these ones are made of intermolecular forces. These ones are covalent bonds that hold these together. These are ionic bonds. And then for metallic, we have what are called metallic bonds. So we kind of have four major structures. We have ionic, metallic, covalent network, and then molecular solids. And those all kind of utilize a different type of bond to kind of hold themselves together. So we're really going to focus on mostly the first two. We've already talked about intermolecular forces a lot. You guys are sick of it. We're not really going to touch that. Covalent networks are just giant structures of covalent bonds. So we're going to talk about this when we get to polymers at the end of the chapter. But by and large, we're going to focus on ionic and metallic solids because those are going to be kind of the new ones for us to be working with. Furthermore, we can kind of classify so all solids kind of have two options. They can either be crystalline or amorphous. So crystalline means that they have regular repeating structure. And this means they're kind of randomly put together. So again, we're gonna go to the Google for this because these drawings not only take a long time, but Google has better stuff. So let's see. Yes, so just like we can see here, a crystalline solid is nice and orderly. It's got regular repeating units. So for example, in this one we have this hexagon pattern here that's just repeating over and over and over again. An amorphous one just kind of has stuff all over the place. So there's not a lot of regularity here. Or you can see it here. Crystalline solid again, everything's nice and aligned. Amorphous ones we have kind of stuff all over. And yeah, you can kind of see it's the same idea here. Nice thing, random thing. Ooh, and this is bad. Someone has apparently written the wrong ones on this. Very clearly, this is the crystalline one, right? This is the regular repeating, and this is the amorphous one. So this is bad, Google. Okay. We're going to see that crystalline ones can adopt any number of fun shapes. Actually, I think I saw a better one up here. Yeah, we're going to look at this in just a second. I'm going to let Oz outside because apparently he's barking to go potty. So 1 second. Okay, so he's outside now. So we're going to have all these different kind of shapes that we can make out of these crystalline materials. So both metals and ionic compounds will typically have what are called these unit cells. And if we were just to look at some of these, this is kind of a generic example. So we have the edge size and then the angles between those. We can see we can have a cubic structure. This is going to be the one we're going to focus on, is the cubic structure. So all the sides are the same and all the angles are 90. We have other ones that change some of these properties. So tetragonal ones have one side that's longer. Orthorhombic ones have all the sides are different, but these are all basically rectangular in origin, so they all have 90-degree angles. We have ones that have kind of an incline. We can have hexagonal ones. We have ones that are more like rhombuses. And then triclinic is everything is different. So these are just kind of options. But we're really going to focus on cubic structures here. So we're going to learn all these sorts of different ones here. Actually, this might be a nice picture. So we're going to see kind of simple cubic ones. We're going to have body-centered and face-centered cubic that we're going to talk about. So let's switch back to our regular screen here. So I don't need you to, again, memorize anything like that at all. We're going to focus on cubic ones. So if I draw our ionic structure from before, this is going to just be in 2 dimensions because my artistry skills are just so good. We can see here that if we just pretend this is in 3D, so like the layer behind it would be the opposite, where we would have blues where the greens are and then greens where the blues are, if that makes sense. We're going to see that this is going to kind of be what we would call a unit cell. So it is the smallest kind of repeating unit over and over. So if we try and look at this structure, we can kind of keep doing that. The unit cell will always be the same for the entire structure. So we can see here what our unit cell looks like. So the unit cell is the smallest repeating unit of a crystalline solid. So for us, again, I'm going to go ahead and just expand that 3-dimensionally. For us, this particular structure that I've drawn up here, okay, I can do this. I can do cubes, I swear. Oh, I'm missing one, aren't I? There we go. Okay. Okay. And then we have the green blob in the middle. Okay. Oh, I guess these should have been connected down there. Hold on. I'm so good at drawing, you guys don't even know. Yeah, there we go. Okay, it's a cube with a green blob in the middle. I'm so bad at these. Okay, you know what? Back to Google here. This is what I'm trying to show you guys. Here is our green blob in the middle is this purple one, okay? So we have our kind of cubic structure with, for me, it was blue atoms or on the outside or ions, and we have a purple one in the middle. Actually, this is a pretty good drawing here. Let's look at this one. So the unit cell, as we can see, is the smallest kind of repeating unit within this. I know I'm so good at this. But we see, of course, it does expand. It does expand in all the directions. So there's ones on top, there's ones behind, there's one to the side. You know, so these crystal structures repeat and repeat and repeat. So we can look at them one by one, basically. So back to my lovely drawing. This is an example of what is called a body-centered cubic structure. So we have a cube with one entire atom in the middle. So that is a cube with atoms at all vertices, which we call lattice points, by the way. And one atom in the middle. If we look at these, if you want to use your geometric skills, how much of each blue atom is actually in this cube? If we assume that the atoms are going to be spherical, how much of a particular, vertex blue atom there is going to be within the cube? If we think about it, we're kind of just looking at something like this. We're looking at one of these, but also expanding it Yeah, Kevin's got the answer as always, but expanding it either towards us or into the page there. And again, let's see if yeah, okay. Back to this. If we're looking at this atom right here, this black one, we can see it is a part of 8 different unit cells. So it is part of these 4 down here, and it's also part of the 4 above it. So that atom is participating in 8 unit cells. And so since all these cells are going to be the same, we're going to see that that atom is going to have 1/8 of its kind of total volume within that unit cell. So vertex atoms, they're going to have 1/8 per unit cell. And so if we take a look at that unit cell again, we can see we have 8 blue atoms in it, right? We have 4 vertices per kind of level, and we have 2 levels. So that's 8 total, 8 lattice points times 1/8 each will equal, we have 1 blue atom total within this thing. If we look at the green atom, we already know we have 1 atom in the middle. And so overall, we're going to see that this structure has 2 total atoms per cell. Does that make sense? So each of the corners here has 1/8 of itself within the cube. There's 8 of those blue things all together. So 8 times 1/8 is 1. And then we have the green one in the middle. And so that's going to be how we get 2 atoms per cell there. All right. Let's look at another thing we can look at. Let's take a look at that atom on the outside there. If we're looking at it, how many atoms is it kind of like bonded to? I'm going to put that in like air quotes, but if we look at this atom in the middle, how many kind of lines are there connecting it to other atoms? We see we have 1, 2, 3, 4, 5, 6. Yeah, exactly, Shade. Perfect. So we're going to see that the blue atoms they have a coordination number of 6. So that's how many kind of things that they would be next to. Kind of hard to describe in words, but that is that number. So that is what's called a coordination number, and so this one would have a coordination number of 6. Okay, so let's look now at what we can see with. Let me try to find an expanded one of this so we can kind of see about the green one. That's kind of a disaster. Well, we're gonna see it's the same thing. Yeah. So we're just looking at the ones that it's kind of yeah, here. Let's look at the Google. So if we're looking at it, it's kind of nearest neighbors, as it says, are going to be for the same type of atom. That's what we're looking at there. So the green one would technically be a different atom. So we would be looking at, for example, we're just looking at sodium. We're ignoring chloride. And so we're going to see here that we're just looking at how many sodiums are next to this particular sodium, for example. we would have chloride in the middle or whatever, and that would be the green atom. So yeah, this one is kind of exactly what we're looking at for coordination number. If we were to think about the green one instead, we're going to end up with the same thing. So it's kind of hard to see in this picture. Let's see if we can't find a good one here. It's the same idea though. We would just basically like move our unit cell, and you would see that it also has a coordination number of 6. Okay, and none of these are very obvious for us. Maybe this one. Can we see it here? If we're gonna see that, yeah, this is kind of, they're too big to see in 3D. But look, let's look at this atom right here. We see it has one above, one to the right, one to the left. One is going to be kind of behind it, one down, and then one towards us. Those are going to be the 6. So the central atom will also have kind of 6, a coordination number of 6. Relative to itself. However, if we want to look at it in relation to the other atoms around it, we could see that it's actually connected to 8. So if these ones up here are all sodiums, this one in the middle is chlorine. Chlorine is connected to 8 sodiums, but there's going to be 6 chlorides around it. So does that kind of make sense? Maybe. So chloride in the middle, 8 sodiums connected to it. If we look at sodium, sodium would have 6 sodiums next to it, and it's going to have 8 chlorines connected to it. So it just kind of depends on what you're looking at in relation to this. So whatever one you're looking at, if you're looking at a sodium related to chlorine or chlorine to chlorine, your coordination number would be different. So if we have different atoms, so this is to each other, but they have a coordination number of 8 to the other atoms. So that's kind of what I'm meaning there. So if we're looking at, this is sodium to sodium, this is sodium to chlorine. So we're going to see that that's going to be the case for... actually, I don't think sodium chloride is body-centered cubic anyway. Cesium chloride is. So let's switch that out. So that's kind of what we're looking at here. Most often, this is kind of the more important one. Just so you know. For whatever reason, that's just kind of the one that's in between the different types of atoms that's typically more looked at. Okay. Let's look at an easier one. Let's look at just simple cubic now. This one would be sodium chloride. Get ready for the drawing. Okay, we can do this. Okay. Black one there. Blue one here. Still quite ugly. I guess I should draw them kind of more of a profile rather than this like directly above view, but whatever. So good at these. If we look at this one, if we look at this this kind of unit cell here, if we look at the black atoms or ions versus the blue ions, So these are all, so vertex atoms will always be 1/8 within the cell for a cubic cell. So we're going to see that we have 4 black atoms times 1/8 of an atom each. So we have half of a black atom or ion per cell. And we're going to see for the blue one, it's going to be the same. Overlapping squares. I mean, these are kind of overlapping squares. I mean, this is how I've always, I guess, learned to draw a cube, and then you kind of have this stuff in the back. But for whatever reason, when I try to throw atoms in there instead, everything just goes to hell. So, or do you mean like something like that one? That one is prettier, that's for sure. So yes, I guess I do know that one, but again, difficult. Like, fine. You want to try this? Okay, let's try it. We'll have fun with this. Okay, blue. Okay, let's see. Did we get it? I guess that is prettier. Fine, you win. Well, even so, these lovely drawings still have the same same properties here. So overall, we have half of a blue plus half of a black, which means 1 total atom per cell. Okay, first of all, I'm definitely Slytherin, so in fact, I'll be taking points away from that. I mean, you should know, first of all, this is pretty much potions class, right? So, yeah, you got the wrong horse there, buddy. Okay. If we look at coordination numbers, if we look for blue to black, if we expand this, which I'm not going to even try to do, but if we pretend that there are other unit cells around it, and we're looking at a black one and seeing how many blue ones are around it, how many blue atoms are going to be touching this black atom here? So if we're looking at this one, we can see very clearly we have 3 blue of them at least, right? We have that. And we're just going to have the same ones on the opposite sides. So there's going to be a blue one above it, a blue one to the right, and a blue one coming towards us. And so indeed, yeah, we're going to have 6 overall there. All right, and since these are different atoms, we don't typically look at the blue to blue or black to black, just because they're going to be alternating in this. So it's not as important to look at those. Whereas the body-centered cubic, we typically would have one type of atom on all the vertices and one atom in the middle of different types. but for simple cubic, you just typically alternate. So it's not as necessary to look at anything else besides blue to black there. Alrighty. Well, let's look at the last one and then we'll start our geometry class for the day. The last one we have is face-centered cubic. Alright, this is going to be the toughest one yet to draw, but I'll try. Well, here, this is what we'll do. We'll do the damn squares. I'll make it nice and big. Wow, that's actually a very nice cube, isn't it? I should get an award for this. Alright, here we go. Here's our cube that is currently simple cubic. But we're going to see that all of the faces of the unit cell here will also have an atom in there. So we have atoms on all of the corners, all the lattice points, and we also have an atom that is kind of right in the middle of the kind of faces of the cell. So if we look at the, if we switch back to Google real quick, for face-centered cubic, we can see here that we have half of an atom, because half of it's going to be in the wall of one unit cell, and then the other half is going to be in the next unit cell. We still have our 1/8 of all of the spheres in the corners, and we can see we have 6 of these kind of half ones in there. So do we see kind of how this is arranged? So we have our 8 lattice points, because it's a cube. We have 6 faces in a cube, and each of those faces has an atom in it that has got half of its volume inside the sphere, inside the cube. So again, we have, for green, we have 8 vertices times 1/8 each, which is 1 atom. We have 6 faces, and all of those are going to be a half atom per face. And so that's going to be 3 atoms. And so the total is going to be 4 atoms. If we want to look at this in terms of coordination number, let's see. Let's see if we can have a nice something with. Oh god, this is just confusing. Is this? Oh, it's hexagonal. Forget it. Get out of here. Where's a nice big old face-centered cube? I guess we're gonna have to stick with this one with all the blobs. Yeah, none of these look nice. Okay, fine. Back to the same picture. If we look at it, let's try and take a look at one of these. What color is this? Kind of beigeish orb. And let's see how many blue ones is it going to be coordinated to. What is our coordination number going to be there? Actually, maybe I could just type in coordination and see. Let's see if we can see the coordination very nicely. Let's see if we can't find a face-centered cubic structure. I mean, could you imagine me trying to draw one that we would be able to use? It would never work. Is this face-centered? No, that's body-centered cubic. These are apparently impossible to look up nicely. Wow, how kind of annoying. I want to show you like nice and obviously what it would look like. Okay, well, okay, let's go back to normal then. So, God, I can't believe I'm going to try and draw this. Okay, I can do it. Okay, one more. Okay. We're just going to look at one green atom here. We have face, 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 face. Oh, I didn't draw enough dimensions. How silly of me. Oh. Why is this so complicated? I bet you guys are all laughing, watching me struggle with basic art. This is just getting so ugly, too. It it might not be bad, but now I can't see the individual cubes anymore, so I can't tell what I've drawn. Oh my gosh, what a mess. I think this is one of them. Okay, well, whatever. The answer is 8. Okay, you know what? Here, this is what we're gonna do. Problem solved. There's no more of this. It's gone. Yeah, it's 8. So we will just accept for blue to green that this is 8. Okay, so yeah, right. It's just a disaster. Wow, that was awful. So yes, the answer is 8 there for blue to green. If we're looking at green to green, we're gonna have 6. If we're looking at blue to blue, it's gonna be don't remember. Who cares? Let's just look at blue to green. All right. Now I'm upset, so we're gonna have to do geometry time. Let's see. Let's go back to our simple cubic structure. All right, and I'm gonna kind of draw. Wow. Oh no, this is awful. Okay. So, these are so bad. Okay, the point here is that in a simple cubic cell, why did I do that? We have Google right here. We essentially have, yes, it's SpongeBob. These we are basically having it such that the atoms touch each other. In a cubic cell. And so we're going to see that we have the radius of an atom is going to be half the side of an atom. Or side of the cell, rather. So does that make sense here? If I just kind of redraw it with one of the atoms in there. Oh no, I didn't do Shane's method. I guess it's been just a long time since I've had to do a sphere. Okay. Or a cube, rather. So this distance we call A. And we are going to see that this distance is R. Right? So the radius of our atom there, we're going to see that two of these R's would be equal to A, right? I can blame you if I want to. So, if we want to think of the volume of the cell in terms of R, it's not too bad for this, right? We know that if A is equal to 2R, and the volume of a cube is just the side cubed, we would get, of course, 8R cubed would be the volume of our sphere. Not sphere, I'm sorry, unit cell. That's what I'm trying to say. All right, and if we looked at our simple cubic structure, we saw that we had one atom, right? That for per cell, right? And if we assume our atoms are the same size, if it's something like sodium chloride, they might be a little different, but we'll be fine. If we're to assume they're all the same size, the volume of an atom is, if we're assuming it's spherical, would just be the volume formula, right, for a sphere. So, with that in mind, we're going to be able to see what kind of the packing efficiency is going to be. How many atoms can we fit into this unit cell? Like how much of it is going to be empty space? How much of it is going to be actual atoms? So here's our information. We have the volume of the cell, which is 8R cubed. We have the volume of the atom, which is 4/3 pi r cubed. And now we also know that we have one atom per cell. So if we want to see how, kind of the ratio for the atoms to the cell, we could see that, kind of the occupied space would be just these two kind of times each other, right? So we already know we have one atom per cell. So we know we have one atom, and we know we have one cell. So plugging these in, r cubed, of course, cancels out. I guess 4 kind of cancels out. So this becomes... Wait, can I do that? Yeah, that works. So that becomes a packing ratio of pi over 6, right? Which is... If we want to put that in percentage terms, let's go ahead and do that. Which is about 52%. So a simple cubic cell has a kind of packing amount of 52%. So that means that 48% of the cell is empty space and 52% of the cell is actual atoms. Hooray. Does that make sense how we did that? We're going to do it for the others, where the geometry actually gets more fun. Simple cubic is boring, right? Nobody likes to do that. All right, then let's go to body-centered cubic. So we had for body-centered cubic, we had 2 atoms per cell, right? That's the factor we're working with. Just tell us the numbers. No. We'll do this one together, and I don't know. I didn't see a good worksheet for these, so I think we'll just go over them together. There's not really any. I mean, it would take way too long to do this on an exam anyway, so I could just give it to you for homework, or we can work through them together in class. Let's just do the opposite, because nobody wants to do this by themselves, and nobody wants to grade this either. So let's just go ahead and do it together. Okay, body-centered cubic. So we also know that, of course, our V for the atom is still 4/3 pi r cubed. However, our volume for the cell is going to be different this time. So if we look at one face of this, we have our blob here. Last time, because the atoms on the corners touched each other, God, this is just so hard to draw. Okay, there we go. Because the atoms touched each other, you could just say that the side of the cube here was just 2 times the radius. However, our radius does not connect here. So we, of course, have one radius, but we also have a missing part. So we're going to have to actually calculate A now using geometry. However, we can see that this diagonal is going to be 4 of the radii, right? So the one that's in the middle of the little, what's it called? Cubic thing. Cell. There you go, unit cell. The one in the middle is going to be touching all the outside atoms. So, in fact, this I think I've drawn it in two dimensions, not in a good way. So, sorry, we're going to have to go to 3D for a sec here. So it's actually this diagonal that is 4R. So from one corner to the other corner. So we're going to have to first figure out what this one is going to be. And then from that, we can then figure out what our A is going to be. So we know that A is the length of the side of our cube. But we don't know what this X is. And so, yes, we're going to have to use our geometry knowledge here. So, this triangle here that I've drawn by... wait, no, this is... Oh, yeah, I can do that like that. It's just a triangle. What are the angles going to be here, do we think? Indeed, they're going to be 45, 45, 90 triangles, which I can't ever draw. There. So this one here is our 4R. This one is... something's gone wrong here. What? This is not a 45, 45 triangle that I've drawn. What is the problem with this? Where's the 90? Is it just because my drawing is ugly? I think so. Because if this were the case, we could just solve for A directly, and that's not how this works. Oh no, I've been stumped on geometry. Okay, we'll figure this out. So, this must not be right over here. So, because we don't know that angle yet, or that amount. Okay, what the heck? Yeah, no comment for sure. I hate geometry, apparently. Body-centered cubic. What is this? Cell edge length. There we go. Let's see if we can find an image that shows me the right triangle. So, I mean, it is exactly what I've drawn, but... So it is what I've drawn, but it's not actually going to be so nice. So this is... So we do have our 90-degree angle right here. The thing is, this should be 45 degrees, but it's not acting like that. So it must be... This must be a 30, 60, 90 triangle then. Because something's weird with this. Don't we love geometry? Yeah, forget this. Yeah. Aha. Oh, obviously we don't know the angles. That's what's wrong here. We're going to have to use two different triangles to figure this out. Well, you know, forget it. Let's just do this tomorrow. I'll look up our geometry so I don't have to kind of... I'm not sure it will be isosceles, because isosceles, a right triangle, would be 45, 45, 90. But I think this is actually one that is not 45, 45, 90. We're going to see that will be the case for the face-centered cubic, but not for this one. So we'll do this tomorrow, just because it's quite silly that I have forgotten the geometry rules here. So it is a scalene triangle. So I'm thinking it's 30, 60, 90, but I'll double check that. So we'll have that for tomorrow. Okay, cool. So you have homework on intermolecular forces. That is up on Canvas, so you should be able to see that due Sunday. Tomorrow we will continue with this. Aha! That's what I'm looking for. Yes. Well, never mind. How curious. Yeah, so it's 30, 60, 90. But anyways, we'll deal with that tomorrow. Yeah, cool. Have fun. We'll see you all then. We'll continue our geometry lesson where we will never want to ever look at these again. But you know what? We can say we covered them. So that's all that matters, right? So there we go. So I'll put these up and you'll be all set. Alrighty. See you all tomorrow for more geometry disasters and exciting times. So, bye-bye.